I now call to order the Society's 2,495th meeting in what is now the 153rd year since its founding on March 13, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by David Spergel. The Society is grateful to PSW Full Year Series sponsors PSW member Mike Helton and Helton Associates LLC for their support. Thank you, Mike. And we are also grateful to PSW Michael Sandifer for sponsoring tonight's lecture. Michael's not here. He's suffering in France. I am pleased to note that the following new members have been admitted to the Society. Sarah Damiani, a clinic director interested in math, physics, and cosmology, and medical and health sciences, who learned of PSW from a member. Morgan Gendel, Star Trek writer and aerospace entrepreneur, interested in planetary surface habitation, who learned of PSW from PSW member A.C. Charania. Michael Haggerty, Chief Marketing Officer at Presna, interested in nanotechnology, high-performance computing, advanced materials, and artificial intelligence, who learned of PSW from PSW Larry Milstein. And tonight's speaker, David Spergel, who learned of PSW from PSW member Casey Lease, and from our invitation to him to speak here tonight, and whose interests will be only somewhat clear to you from tonight's proceedings because he has a lot of interests. If you are interested in joining PSW, you can access a membership application form on the PSW homepage. At the upper right-hand corner, you'll find a blue join button, and you click on that and follow the prompts and submit your application. You can also access the application form using the business card QR codes at the back of the room. Please help yourself to those cards and give them to all your friends and ask them to look into PSW and see if it would interest them. All members are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, which is the former name of PSW Science. And if you choose, you can also purchase and wear a ribbon emblematic of the Society. And if you have not received your signed copy, if you're a new member, please see me after the lecture. Recording Secretary Scott Matthews will now present the minutes of the 2,494th meeting and the lecture by Richard Pyle on deep sea coral biodiversity. Scott, the stage is yours.
Thank you, Larry. Good evening. On April 19th, 2024, in the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,494th meeting of the Society to order at 8:04 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Philip Duchamp titled, "We Have You Surrounded: Encapsulation and Its Application to Vaccine Formulation and Drug Delivery." The minutes were approved as read. President Milstein then introduced the speaker for the evening, Rich Pyle, Senior Curator of Ichthyology at the Bernice Powahai Bishop Museum and Director of XCOR. His lecture was titled "Diving Deep into Biodiversity, Leveraging the Latest Technology to Explore Deep Coral Reefs." The speaker began by presenting a metaphor of a burning library and the firefighters trying to both put out the fire and save as many books as possible. He then went on to discuss biodiversity and the fact that the DNA of every species contains information that has been passed down for billions of years. Therefore, he claimed, each species can be thought of as a book, and biodiversity can be thought of as, quote, Earth's greatest library. Climate change and the increasing rate of extinction is therefore analogous to the burning library. Pyle emphasized the fact that conservation is as much about preserving unknown species as it is preserving known species. He indicated that because about 99% of the Earth's habitable ecological volume is in the oceans are the most important place to scout for unknown species. He noted that humans have had considerable success cataloging biodiversity on land, but that we have barely begun to explore the extent of marine biodiversity. He said, quote, as terrestrial mammals, we have been limited to the briefest excursions to the shallowest depths, unquote. Pyle explained that his primary goal as director of XCOR, the Center for Exploration of Coral Reef Ecosystems, and senior curator at the Bishop Museum is to leverage modern technology to overcome these limitations and extend the range over which humans can explore marine biodiversity. Pyle then discussed the mesophotic coral ecosystem, the so-called twilight zone, between 50 and 200 meters depth. This region is generally too deep for conventional scuba and too shallow for most submarine expeditions. He described how mixed gas rebreathers allowed he and his colleagues to explore this twilight zone more extensively than ever before. He then discussed other technologies that have increased the range of human exploration in the maritime environment. These included submersibles coordinating with human divers, human-controlled underwater robots, autonomous underwater robots, 3D imaging, stereo videogrammetry, and environmental sensor arrays. Pyle claimed that the XCOR project has discovered close to 1,000 new fish species and is finding them at a rate of 12 new species per hour of bottom time. He said that XCOR is responsible for creating ZooBank, the official online registration system for scientific names of animals. He ended his lecture by saying, quote, we cannot afford to continue the status quo in battling the fire that engulfs the global biodiversity library. The lecture was followed by a question and answer session. A member asked how the data being gathered by XCOR could be used to guide decisions and policy moving forward. Pyle responded first by saying that this data could be important for genetically modifying certain species, particularly coral, to be more robust or resilient to climate change. But he doubted that such efforts could be implemented on a scale that would make a difference. He went on to say that there are too many, quote, unknown unknowns, and that we therefore do not know in advance what the value of this data will be. A guest asked about efforts to look for the species of folklore like the Loch Ness Monster. Pyle replied that the Loch Ness Monster was not on his radar, but that folklore plays an important role in his work. He said that in several Pacific Island regions, the indigenous knowledge of fish species vastly exceeded what scientists understood, and that the oral history and folklore of local peoples has benefited our understanding of marine life. A member asked Pyle if he and his team are studying cold water, deep species of coral like the ones living off the coast of Norway. Pyle responded that these corals are essentially monocultures and are therefore less interesting from the point of view of biodiversity. A member asked why there are more endemic species on deeper reefs than in shallow waters, and what effect that would have on loss and recovery of biodiversity. Pyle responded that the likely mechanism is related to glacial cycles and the rise and fall of sea level. Shallow coral reefs tend to form on sloped regions of the seafloor, while deep corals tend to grow on more vertical structures. As sea level rises and falls, the shallow coral habitat appears and disappears, whereas the deep coral habitat can rise and fall with the sea level like a tide gauge. He said that the endemic species are the most sensitive in terms of biodiversity loss because, by definition, they only exist in one place. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,494th meeting of the Society at 10:07 p.m. Eastern Time. Temperature in Washington, D.C., 13.9 degrees Celsius. Weather, cloudy. Audience in the Powell Auditorium, 73. Viewers on the live stream, 35, for a total of 108 live viewers. Views of the video in the first 2 weeks, 301. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any additions, corrections, or comments on the minutes? Hearing none, I will accept a motion from a member to accept the minutes as read. A second. All members in favor? All members opposed? Minutes are accepted as read and will be posted to the website in due course. Anyone who is only able to access the recording of the minutes and has some comments can send them to corresponding sec at pswscience.org, and they will be taken into consideration and appropriate correction made if necessary. And we now turn to tonight's lecture by David Spergel. David is the president of the Simons Foundation. Previously, he was the founding director of the Center for Computational Astrophysics and at the Flatiron Institute, and chair of the Department of Physics at Princeton University. He was a leader on the Wilkinson microwave and isotropy probe, WMAP, which measures the age, shape, and composition of the universe, and he served as co-chair of the Roman Space Telescope, originally known as WFIRST Science Team. He's an author on over 400 science and technical papers, served as chair of the National Academy's Committee on Astronomy and Astrophysics and the National Academy's Space Sciences Board, on the NASA Astrophysics Subcommittee, and on the NASA Advisory Council. Among many other honors and awards, he has been awarded a MacArthur Fellowship, the Breakthrough Prize, the Gruber Prize, and the Shore Prize. He's a member of the American Philosophical Society, the National Academy of Sciences, and the American Academy of Arts and Letters. And he is a fellow of the American Physical Society and the American Astronomical Society. And of course, as of tonight, he's a member of PSW. He earned a BS at Princeton University, spent a year at Oxford, and then earned a PhD in physics at Harvard. As usual, all questions will be held until after the lecture, when we will have a Q&A session that typically will last until we have no more questions. Please keep in mind our media policy. You are not allowed to film the lecture. You may avail yourself of PSW's recording of the lecture, which is going to be available for free to anyone who wants to watch it on our YouTube channel, our Vimeo channel, or via our website. And with that, David, the stage is yours.
So it's a pleasure and an honor to be here. I'll begin by talking about a couple things that I won't talk about in the talk. So what I will not talk about, but happy to answer questions about after the talk, is what is the Simons Foundation? What is it like to be president of an organization that gives out about $700 million a year in support of basic research, math, science, work on understanding autism, supporting Quantum Magazine, movies, and so on. Sandbox Films, things like Fire of Love are among our movies. So that's been a very interesting day job, learning all those roles. I also won't talk about in my talk, but happy to discuss something that I've gained a little bit of media attention for over the last couple years, which was chairing NASA's Committee on Unidentified Aerial Phenomena, later renamed Unidentified Anomalous Phenomena. So Larry asked me to answer questions on that as well. And after we talk about the cosmology questions, happy to turn to that at the end. What I will talk about is what we have really learned about cosmology, about our universe, over the past 20 years or so. That our universe is both remarkably simple and remarkably strange. And I want to focus particularly on the role that our observations of the microwave background, the leftover heat from the Big Bang, has played in shaping this. And it's a pleasure to be joined by my longtime colleague, Al Kogan, from Goddard Space Flight Center. Al is one of the people who has played a major role in observations that I'll talk about, starting with the COBE mission and has also been part of the WMAP mission that I'll talk about. So, what's the conclusion of my talk? 5 basic numbers describe all the properties of the observed universe. The universe's age, the density of atoms, the density of matter, how lumpy the universe is, what is the fluctuations in its density from place to place initially, and how those fluctuations vary with scale. And with those 5 numbers, that basically completely characterizes the large-scale properties of the universe. So that's a remarkably simple universe that we live in. But it's also remarkably strange. And this is a situation where we both, in some ways, understand a remarkable amount, in that we have these observations and a very consistent set of theories to explain them. But we don't know what makes up most of the universe. Atoms, the stuff that makes up us, makes up less than 5% of the universe. Most of the matter in our own galaxy is in the form of dark matter. That's stuff that gravitates like ordinary matter. Best guess is that's probably some new form of subatomic matter, subatomic particles that we've not yet detected. There is lots of effort to try to figure out what that is. I actually worked on that problem since my PhD thesis. Even more strange than dark matter is dark energy. There seems to be energy associated with the vacuum, with empty space itself. We don't understand its value. We don't understand what determines it. We don't know whether it is indeed constant with time, like the cosmological constant that Einstein evoked. We don't know why there's so little antimatter. Our theories of physics are mostly symmetric and suggest that there should be equal amounts of matter and antimatter. And our standard model of physics predicts a slight excess of matter over antimatter, but what we observe is much more than that. And we don't understand basically why we're here, why most of the protons in the universe didn't annihilate with antiprotons. We don't know how the universe began. We'll talk about the expansion of the universe and the Big Bang, but we don't know if time started with the Big Bang or if there was a before the Big Bang. And while we see this signature as a very rapid period of expansion that we call inflation, we don't understand what drove this early expansion. So these are all kind of fundamental questions about our cosmology that we don't know the answer to. So that's going to be, you've now heard the conclusion of my story. We'll come back to it. And to understand it, we're going to start by talking about special relativity. And special relativity basically says light travels at a finite speed. You see me, not as I am at this moment, but as I was a few nanoseconds ago. because it takes light a few nanoseconds to get from me to you. And the further back you are in the room, the further back you see me in the past. This is not a big effect. I don't change that much on the nanosecond timescale. We see the sun as it was about 8 minutes ago. We look out to Mars, depending on where it is in its orbit, it could be more like 30 minutes. There's a wonderful scene in the movie The Martian where you sit patiently waiting for that signal to come from Earth to Mars and back, because it takes, time for that signal to go back and forth. When we talk about a star being 4 light years away, that means it takes light 4 years to travel from that star to us. So we see that star as it was 4 years ago. And the typical stars we see in the night sky might be 50 or 100 light years away. So they see us, if you were orbiting those stars, as we were 5 light years ago. So as we look out in space, we look back in time. And that really makes us kind of historians, that we are looking back at the universe's evolution. We don't get to do experiment. We don't get to make multiple universes. We get to observe what we can see. And in some ways, I think we're much more like classicists who get passed down bits of ancient history that they get to find and try to construct a coherent story from what they see. We have an advantage in that seems to be that physics is much simpler than understanding humans and history. And the universe seems to be really simple. And ultimately, we can rely on aesthetics and extrapolation from what we learn in the laboratory to construct a model of our past. And that's sort of the basic idea behind what we do as physicists approaching cosmology. So that's special relativity. And the key concept when I talk about mathematics and sort of the picture we have is one of these remarkable facts about the universe, that mathematics turns out to be the language of the universe. And this is from Galileo, who wrote that the universe cannot be read until we've learned the language and become familiar in the characters in which it is written. It's written in a mathematical language. The letters are triangles and circles and other geometric figures, without which means it is humanly impossible to comprehend a single word. And that's how Galileo constructed his understanding of physics. And Wigner, one of the great physicists, talked about this in terms of the unreasonable effectiveness of mathematics. And I just love this quote, that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift that we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research, and that it will extend, for better or worse, to our pleasure, even though perhaps to our bafflement, to even wider areas of learning. And this mathematics that underlies our theory, the fact that it's going to work on the scale of the universe, to me is one of the really remarkable things, that this universe is so simple and mathematics works on these large scales. And while Galileo constructed his theories using triangles and squares and shapes, Einstein would use differential geometry to construct his theory of general relativity. And his goal was to replace the idea of action at a distance, which is kind of strange, the idea that the sun pulls on the earth through some mysterious force, which is the way Newton described it, with the idea that matter curves space around it. And Johnny Wheeler, who is my academic great-grandfather, summarized general relativity as matter tells space how to curve, and the curvature of space tells matter and light how to move. And this was tested by the Great Eclipse Expedition of 1919, when Eddington went and observed a star behind the sun, And instead of seeing the star in position position B, where he saw it in position B. The light was curved and the star position moved. And this was nicely summarized in the New York Times. It's that. Oh, yes, there we go. Which said, lights all askew in the heavens. Men of science, in those days was mostly men, more or less agog over the results of the eclipse. And here's some false, fake news in the New York Times. Stars not where they seem to be or calculated to be, but no one need worry. In fact, the stars were exactly where Einstein calculated them to be. And that was the great triumph of general relativity. Now, Einstein then took that theory of general relativity and tried to apply it to the whole visible universe. He did this by making some aesthetic, simple assumptions. He said the universe would be homogeneous, uniform everywhere, the same in all directions. He had no observational evidence for this. He just chose that because it was the simplest aesthetic idea. And, as we often do as physicists, he thought he could solve those equations. If it wasn't that way, it'd be too hard to solve. He didn't know enough differential geometry. Many years later, we have lots of observations showing the universe is on its largest scale, uniform, homogeneous. So Einstein made the right assumptions based on aesthetics. He realized that that would predict that the universe is expanding. This bothered him because as far as he knew, the universe should be static. And he didn't want a universe that was changing with time. And here's where his aesthetics went wrong. Because Hubble would soon observe that our universe was indeed expanding. And this, I think, by the way, is the most conceptually difficult part of the talk. Because most of us have a Euclidean notion of space and time. And you say the universe is expanding. The question I think many of you have is, what is it expanding into? I think the best answer to that is it's expanding into the future. And the way I like to think about the expansion of the universe is to suppress one dimension, to think about us and the Milky Way and all the other galaxies as living on the surface of a sphere. And each galaxy is a point on the sphere. And when we travel from one galaxy to another, we're moving along that sphere. And that sphere is expanding with time. So the radius of the sphere you can think about as time. So as the universe gets older, the sphere gets bigger and bigger. The galaxies get pushed further and further apart. The universe gets less and less dense, colder and colder as it stretches. And we can take that picture and now run it back in time. As we go back in time, the sphere gets smaller, its radius decreases. Galaxies get closer and closer together. The universe gets hotter and hotter. And eventually we can collapse that sphere down to a point. That's called the initial singularity, when the universe reaches its maximum density. That's the moment of the Big Bang. And as you think about that collapsing sphere, you see the Big Bang didn't happen in a place. It wasn't a place in space where the Big Bang happened. It was a moment in time. It was a moment in time when the density reached maximal density. And that moment, roughly 13.8 billion years ago, happened everywhere. The whole universe reached that density at the same time. It all collapsed down to, at that moment, to the point. And one of the big questions, which I already hinted at, is you look at this and say, well, what was before then? And we have two broad sets of answers. One is to say there was no before then. Time started at that moment. And asking what was before the Big Bang is like asking what's north of the North Pole. Someone says, can't you keep going north? No, you've reached, that's as far as you can go. And it may be that was the moment that time began. Another possibility is there was something that happened before then. Maybe it's a quantum foam, as some people have proposed, or maybe the arrow of time reversed, and had, instead of a expanding universe, a contracting universe. And we could go through that Big Bang and have what people call a bounce, and the universe was maybe contracting and then reaching a maximum density and bouncing again. And one of the big open questions in the field, it was what was there before? And we, at the moment, don't know. And I've already mentioned this big mistake and how we added this cosmological constant. And here's some of the first data to show the expansion of the universe. This is data taken by Edwin Hubble, of whom the Hubble telescope was named after. Here's Einstein looking through the telescope where the data was taken in Pasadena. And this shows the modern version of that data, showing as you get further away, galaxies get dimmer and dimmer. The universe is indeed expanding. So now let's talk about our basic model. Our basic model says we start out with a universe that's uniform, as Einstein posited first, isotropic, the same in all directions, and we look on large scales, it's about the same everywhere. We start with the simple assumption that the laws of physics that we observe in the laboratory are valid not just in our lab, but everywhere else we look. And it's something we test by looking at atomic constants across space and time. We don't see them vary. We don't see evidence for the strength of gravity varying across space and time. So this assumption that something that you might discover and measure in a laboratory in Maryland, that we're going to see the same behavior across all space when we look at with the James Webb Telescope at a distant galaxy, is about the simplest assumption we can make. It's one we test and it seems to work. And as I noted, when people started with these assumptions, we had no observational evidence for them. Today we test them a lot, and they seem to hold up pretty well. So based on those assumptions, we can now construct a quick history of the universe. And as I noted, it's a universe that started out very hot, very dense, filled with radiation. As this universe expands, it cools. About in the first few minutes of the universe, most of the deuterium and helium in the universe forms. About 300,000 years after the Big Bang, the universe gets cold enough that protons and electrons combine to make hydrogen. That process ends about 400,000 years after the Big Bang. And when we look out at the microwave background, this leftover heat from the Big Bang, we're looking out to that moment, 400,000 years after the Big Bang, when the atoms first formed. And I gave my title as looking at the universe's baby picture. And that's because we're looking at the universe when it's 400,000 years old and inferring much of its properties from those observations. After about 100 million years, things get dense enough, fluctuations grow enough that stars and galaxies start to form. And then larger galaxies and quasars start to emerge on that sort of 100 million to billion year time scale. And one of the things that James Webb has been doing in the past couple years is really pushing into this time zone between 100 million to a billion years after the Big Bang and learning what's there. But today's talk will be looking further back in time, looking out at the microwave background, looking back to the moment when the universe made this transition from being neutral to being ionized. Now, I'm going to be primarily telling you a story of how everything fits together. But before we do that, I just want to take a brief detour into my own intellectual history, because I think the story we usually tell in science is one of triumph when everything works. But sometimes you have beautiful theories and they don't work. So in the 1980s and early 90s, I worked on the idea that the universe underwent a phase transition. A phase transition is something like water freezing and going from, water where you have no preferred directions to ice. And if you've put water in your freezer to make ice cubes, those ice cubes have little bubbles in them, right? They're not perfect crystals. And that's because you freeze them quickly and you trap defects in the crystals. They haven't reached the ideal lowest energy state of a perfect crystal. There's energy associated with that defect. We think the universe has gone through a series of phase transitions, and there could be energy associated with these defects. And I explored the idea with my colleagues that this could be the seeds of galaxy formation. And this was a plausible, reasonable idea, made very clear predictions. And when NASA launched the COBE mission, measured the first observations of these fluctuations, the variations in density from place to place at a part in 100,000, observations that would earn John Mather and George Smoot the Nobel Prize a number of years later. I looked at this data and said, we're dead. Realized that what they saw did not fit my simple, aesthetic, beautiful theory. And I want to kind of emphasize that story, both because I think many of us in our scientific paths, sometimes things fail. Sometimes you explore things and they don't work. But that's how we progress. And that's then how I got involved in the next set of observations, which I'll talk about. But I also think because I'm telling one part of the story, which is that the universe is kind of beautiful and aesthetic and that things fit, that sometimes it doesn't fit. So from there, oops, I'm going the wrong way, jumping too far. We developed this inflationary universe model. And this is a model in which the universe did undergo a phase transition. It got trapped kind of in a superheated state. It drove exponential expansion, produced a universe that's large and uniform and nearly flat. And the model predicted a flat universe with fluctuations that were nearly the same on all possible scales. And one of the things we wanted to check about this model is this model made a prediction about the universe's geometry. Now, in cosmology, the universe can have three possible geometries. If the universe had just the exactly right critical density, its geometry would be flat. The sum of the angles of a triangle would be 180 degrees. The geometry that you learned probably when you were about 11 would be valid on the scale of the physical universe. In such a model, if you drew a sphere, the surface area of the sphere would always be 4 pi r squared. If the density of the universe is lower, the density, remember I told you general relativity says matter tells space how to curve? Well, with less matter, it curves less. You get negative curvature. The sum of the angles of a triangle is less than 180 degrees. If the density of the universe was large, we get positive curvature. So this curvature is interesting not just as a mathematical fact, but because it determines the universe's destiny. And if the universe is negatively curved, density is low, it will expand forever, as it will if it's flat. and it will get colder and colder. If the density of the universe is high enough, gravity overcomes expansion, and that expanding universe turns around and collapses in a big crunch. And since it got colder and colder as it expanded, if it started to collapse in a big crunch, it would get hotter and hotter. Now, this was all explained by Harlow Shapley to Robert Frost at the Harvard Faculty Club about 60 years ago. And Robert Frost summarized this by saying, some say the world will end in fire, others say in ice. So if I remember the poem right. I think I've tasted enough of desire to think that the world will end in fire. But I also know enough of hate to know that ice will suffice. And as I'll argue, looks like ice is going to suffice. Our geometry seems to be very close to flat, and because the universe is filled with dark energy, our current best understanding is the universe will just keep expanding forever and ever, getting lower and lower in density, and will not collapse into a big crunch. So how do we address this? How do we figure out what the geometry of the universe is? And at this point, I think we should return to Galileo, who said this wonderful quote, which I think to me is one of our guides of what we want to do as scientists, which is we measure what's measurable and make measurable what's not so. We figure out how to make measurements, and that's what we do. And that's sort of what drives our understanding. Aesthetics is important. You saw as a theorist, we looked at things like these defects. It was a good idea, but Kobe goes and measures it, and then you abandon that idea. So we can measure the geometry of the universe by looking at the size of the fluctuations we see. Nature holds up a ruler to us because when we look at the microwave background, we're actually seeing the signature of sound waves in the microwave background. I'll do an experiment to show how this works. There are fluctuations in density in the universe that produces fluctuations in pressure. So let me create a pressure fluctuation. That's a pressure fluctuation. It sends out a sound wave. That sound wave moves out like a ripple, much like if you're throwing a pebble into a lake and it sends a ripple moving out. If that ripple gets to move for about 400,000 years, the size of that ripple will be about 400,000 light years across if things are moving at close to the speed of light. There's some corrections there for the expansion and so on, but we're not going to do all that. So we know this length here. And if the universe is positively curved, it will correspond to a smaller angle. And if the universe is negatively curved, it will correspond to a larger angle. And if what they taught us in junior high was correct, it should sum to an angle of about a degree. So by measuring the size of these hot and cold spots on the sky, we could figure out the geometry of the universe. And that's what we set out to do. And that was one of our goals when we launched the Wilkinson Microwave Anisotropy Probe, a NASA mission we launched about 20 years ago. In fact, back in 1994, 95, I lived not far from here, because I spent my sabbatical at Goddard working on the proposal to launch this mission, and then worked with my colleagues at Goddard and Princeton and elsewhere to help build and launch this mission and analyze the data. And we went out and looked at the microwave background, looked at the leftover heat from the Big Bang, and this is what we saw. And your eyes are almost certainly drawn to this big red thing in the center. That's the Milky Way. Some of our colleagues are interested in the Milky Way. That's not what we want to study. We want to study this stuff, the fluctuations from the very early universe. And what we did was we looked at 5 different frequencies. At each frequency, the galaxy gets dimmer and dimmer in this range. And then we're able to combine the data to make a clean map. And when you look at the clean map, you discover, hey, Stephen Hawking's initials are there. But that's not really what we studied. We think that's a statistical fluctuation. We don't think the universe was giving us a message about Stephen Hawking. Nor did we think the universe was scratching some obscenity and we were missing 2 letters. But what we wanted to do was measure the statistical properties of what we saw and understand what we can infer from it. And to describe our analysis, I want to go back to those sound waves moving out. And this shows what happens when you've got a density fluctuation with that sound wave moving out. And when you look at this picture, what you see is this region here with an excess of photons and electrons. And that's going to be a hot spot, but you've got more photons. So you've got a hot ring. The interesting thing in this picture is because we posited a model from other observations, actually done based on work that goes back to things that Vera Rubin did here, we knew that there should be dark matter, and dark matter that didn't interact with electrons and protons. And the dark matter is cold and it doesn't move. So while the electrons and photons and protons move out in a sound wave, the dark matter stays here. And because there's more dark matter, it produces a deeper potential well, produces a cold spot. So what we expect to see is cold spots surrounded by hot rings. If we measure the ratio of the cold spot brightness to the amplitude of the hot ring, that tells us the ratio of dark matter to ordinary matter. If we could measure the thickness of the ring, because it's determined by the diffusion of photons relative to the electrons, that gives us the density of atoms. I've already shown that the angular size of the ring, what we see on the sky, gives us the age of the universe. The overall amplitude of the pattern as a function of scale gives us our measure of lumpiness. So you can see by looking at these observations, we understand all the physics we need to extract the basic parameters of the universe. Now we actually end up seeing many, many different waves on different scales. So when we look at our picture, we have to separate it out and stack it. And these are observations from the ESA's Planck satellite, which was a successor satellite that mapped the sky with higher sensitivity. And what you see here is first around stacking up each cold spot and the hot ring around it. And the top panels are observational data. Here's a hot spot with the cold ring around it. This is theoretical models fit to the data. This is the pattern of polarization we see, predicted and observed. And you can see the patterns we see of hot and cold spots match exactly with the data. And this property of sound waves we see not only in the distribution of the microwave sky, but in the large-scale distribution of galaxies. And there are recently results coming from the DESI survey that was reported just 2 weeks ago, which showed an even more accurate measurement of how galaxies cluster, showing the same pattern produced by sound waves. So what have we learned from this data? This represents how we look at our measurements by looking at the amplitude of fluctuations as a function of angular scale. You'll see the fluctuations peak on the scale of a degree, suggesting the universe is flat, giving us effectively a measurement of the universe's age. By looking at the ratio of these peaks, equivalently the ratio of the cold spot to the hot ring, that gives us measurements of the density of atoms, the density of matter. We can see how the fluctuations vary with scale, and we end up with a coherent model that fits all of the data. This is the data as of about 15 years ago, and it all kind of fits together coherently with our theory. And we also see the fluctuations look Gaussian, random phase, about as simple as they could be. And when we extrapolate to the growth of structure and compare to the large-scale distribution of galaxies, this is a numerical simulation showing how clustering grows with time. We can compare what we get when we take our observations of the microwave background, fit our theory to it, to observations of the large-scale distribution of galaxies mapped by galaxy surveys, and the statistical properties all fit together beautifully. We get a very coherent result. Our experimental data continues to improve. I've already mentioned the observations by COBE. These are COBE maps of fluctuations. The data from WMAP, NASA's satellite, launched in 2001. Planck, the ESA satellite, launched in 2010, and its results came out throughout the 2010s into 2020. I'll mention some data we have from the Atacama Cosmology Telescope, which maps the sky at higher precision. And we continue to improve these data. One of the things that the Simons Foundation has funded is the Simons Observatory. NSF, the British funding agency, and the Japanese funding agency have contributed to its upgrade. One of the things that Jim Simons, the founder of our foundation, asked for is that we will get first observations by his birthday, which was 3 days ago. And the team met the schedule, and we now have first observations. They're the first observations, so we can focus the telescope, it all works. We actually know that the detectors are much more sensitive than anything before. So while I'll primarily show you results from the Planck experiment in the next set of data, and some from ACT, we actually now have in hand from the ACT experiment data that's actually 5 times more sensitive than Planck and about 5 times the resolution. A lot of this data is still being analyzed. We do something we call blinding when we analyze our data, where we don't look at the results until we fix every property of the experiment, then unblind and look at it. So I have seen very recently the unblinded results. I actually know what they look like. I'm not allowed to talk about it yet. We will publish these results sometime in the next 6 months. But the data just continues to improve in this series. And this shows the Planck data, able to measure fluctuations on much finer scales than we did with WMAP. And while WMAP measured the sky at 5 frequencies, with Planck, it was done at 9 frequencies. That gave us much more information about the galactic dust, let us characterize it better. And this has been a steady progression. As instruments improve, detectors improve, we can make more sensitive maps. And what's been very exciting to see in some ways, disappointing in others, is as the data improves, the same model that fit 20 years ago continues to fit the data as it continues to improve and improve. And I've seen the new data. I'm still giving the same talk. And, I've mentioned we've been collecting data now from Chile. We go up to 17,000 feet up in the desert. And, here's the Planck results. Here's the same region of the sky with ACT. And you can see this much finer sensitivity. And let me draw your eyes to these things here. These blue dots represent clusters of galaxies containing about 10 to the 15 times the mass of the sun. And these clusters of galaxies are filled with gas. and electrons. And when the microwave photons pass through those galaxies, those clusters, there we go, can cast a shadow. And while you might not be able to see this, you can't see this, but imagine you couldn't see this hammer, this gavel, you could see the shadow it casts. And those blue dots are shadows cast by clusters of galaxies against the microwave sky. And we could actually see every cluster in the visible universe by looking at their shadows. And what you can do with these clusters is take a telescope like Hubble, or now James Webb, point it at these clusters, these spots, and wherever you look, you find thousands of galaxies that make up the cluster. Here we are in Chile, and where we continue to take the observations. This is actually an old picture taken by drone. That's the ACT telescope. Oops. This here, which looks like a construction site, now actually has 5 active telescopes. And they're not just looking at these temperature fluctuations we talked about. They're also looking for the signature of gravitational waves, so-called B modes, that if our theories of inflation are correct, should produce these gravitational waves that have a distinctive signature in the early universe. And if we do get to detect them, and we don't know what we'll see, this will tell us a great deal about the early universe. So let me now conclude. I hope I've given you a sense that cosmologists are historians who try to reconstruct a story of the past based on incomplete observations, and guided by our sense of aesthetic, which sometimes steers us right, and sometimes our ideas don't work. And we try to construct a simple model, and we seem to have one that fits the observations. And while it's simple, it's also strange. It implies the existence of dark matter, dark energy, and as is often true in science, we've answered some questions, things about the geometry and so on. They open a new set of questions, and that drives the next set of experiments and observations. So let me stop there and take questions. Thank you.
As most of you know, we have time for questions now.
Yes, my name is James Coe, and I'm a member. And my question is, you talked a lot about symmetries and simplicity, and I think you must know of the CPT theorem, charge, conjugation, parity, and time. And I'm wondering if the consensus seems to be that the universe is expanding, but if you believe in symmetry, that things don't always go one way, that time might be reversible because many processes are indeed reversible. Do you believe that the universe will continuously expand, or do you believe that there might be some symmetry principle that would tell us that it would again begin to contract, the way you showed in one of your slides, that we could have gone to a negative time possibly?
So that's a very interesting question. And let me take a moment to actually explain CPT for those who aren't familiar with it. So we can look at the universe and say, what would happen if we took the charge of every negatively charged particle and made it positively charged, and every positively charged particle and made it negatively charged? That's charge symmetry. And would the laws of physics change if we flipped all the charges? We can talk about paratree symmetry. If I showed you a movie of everything happening, and then I took that camera and I stuck a mirror in front of it, and you saw everything through a mirror. So everything that was circulating clockwise would circulate counterclockwise. That's switching parity. In time, it's time reversal symmetry. You've seen a movie of two billiard balls colliding, and I run that movie backwards, and can you tell from the movie whether or not the laws of physics are time symmetric? And the laws of gravity are time symmetric. The laws of electromagnetism are time symmetric. The strong interaction that binds nuclei together is time symmetric. I'm holding out one piece of physics for you for a moment. You take all three symmetries called CPT, and you reverse charge, parity, and time. As long as quantum field theory is a valid theory, you can prove that it has to be CPT symmetric. You switch all three. We know that the universe can't be time symmetric because there's more protons than antiprotons. If the universe was time symmetric, it would have to be CP symmetric. That would mean when you switch from positively charged protons to negatively charged antiprotons, which have opposite parity, we'd have to have all physical reactions would have to be the same. And it was actually Andrei Sakharov, the great Soviet physicist and dissident. He was one of the people who really led the opposition to the communist government and was a real freedom fighter. Before he did that, he posited what are called the Sakharov conditions, which is what is needed to answer one of the questions I listed at the beginning of my talk, which is why is there more protons than antiprotons? And the fact that we see this, though we don't understand the details of the answer to that question, we know whatever answers that question requires that the laws of physics are not time symmetric. And it is the weak interaction, which is the interaction involved with radioactive decay, that we know from experiment is not CP violating. So that there doesn't seem to be a time symmetry. The universe does not, the laws of physics are not time symmetric. Yeah.
Well, we have
Oh,
some.
sorry, you have to wait for the mic. Sorry.
Somebody have the red microphone back there.
Yep.
And then we'll go to the blue microphone.
Hello, Matthew Gorbin. Thank you so much for the talk. I had a question that sort of expanded upon the last point you made, where you get new data and it brings up new questions. But first, I'm really curious, what is the unit of lumpiness that you use for your measurements?
Fluctuations in temperature from place to place.
Okay.
And the amplitude of those fluctuations are about a part in 100,000.
And I'm hoping you could maybe speak a little bit to the Hubble tension problem that's been going on and some of your thoughts associated with that.
So one of the parameters we talked about is the age of the universe, or equivalently the expansion rate of the universe, which is called the Hubble constant, which relates, it's actually the slope of that data I showed. And the Hubble constant that you infer from these very simple geometric measurements I talked about with the microwave background is about 68 kilometers per second per megaparsec. So 68 plus or minus about 1. If you look at the galaxy distribution, you get a value of 68 plus or minus 1. And if you look at gravitational lensing, you get a value of 68 plus or minus 1. There's a traditional technique of using what's called Cepheid variables and a distance ladder to make these measurements. It's a technique that has, I would say, a bad history. It got a value of 500 when it was first used by Hubble, because he didn't understand the properties of Cepheids. Then it got a value of about 100. And now it's settled so that the value gotten by Adam Rees and his team is about 72. And 72 is pretty close to 68, but they claim an error of about plus or minus 1. Now, I have concerns about their error analysis. When they talk about these things being 5 sigma errors, they do not marginalize, I think, properly over their uncertainties. what they tend to do is take things like, you can ask, do the properties of Cepheids depend on the chemical composition of the stars? I believe the right approach to that is to vary the possible effects of metallicity, do what we call marginalization. When you do that, that increases your uncertainties. And I think they don't do that in a number of ways. And so I am not convinced of the error analysis. And the analysis with Cepheids is much more complex than the simple geometric things we've done here. So you'd like to see this done by other groups. Right now, there's an effort being led by Wendy Friedman at University of Chicago, who's using the James Webb to use multiple methods to measure that scale. So remember, we get 68 with the linear theory cosmology methods. 72 is the Cepheid value. That's the Hubble tension between those two. Wendy Friedman has not published her results. Her team reported results in Chicago 3 weeks ago. I wasn't there. I've been told that she has reported a value of 70, kind of right in between, with enough uncertainty that we can't yet distinguish between, is her value consistent with the value of 68 or 72? This is something that depends on the number of galaxies you observe with Cepheids and similar methods. The results she reported was based on the first year of James Webb data. They continue to take more and more data. And this is a discrepancy that will either go away, which will be my personal bet as the data improves, or if it worsens, it would suggest that the story I've told is incomplete and there's some additional physics needed. The most likely new physics would probably be that the properties of dark energy is more complex, that it's not constant and it varies with time. That would be fascinating if true, but we'll see.
We'll take the blue microphone, and can you bring the red microphone up here to Dorema? Keep your hand up, Dorema.
Hi, this is
Keep your hand up. Scott.
me.
Okay.
Oh.
Carl.
Yes, hi, this is Carl Merrill, a member of the Society. That was a spectacular summary of the early universe. But it raised a question. I think it was in 2014 we had a lecture here on the results of BICEP 2 and the effect of the dust, the galactic dust, and the idea that perhaps by looking at different wavelengths, we might be able to see what they were trying to look at in BICEP 2. And it looked like what you're building in, or what they're building in the Acme Desert with the 5 telescopes is going to try to address that. And I wondered if you could amplify some of what they're doing and what happened.
Yes, so this is something that's very much part of my own personal intellectual history, I'll put it that way. So the BICEP 2 experiment, which was actually led by one of my former undergraduate students, reported the detection of gravitational waves in 2014. And when they did that, it was done at a single frequency. And they did that based on using some Planck data that they scanned off the web. It was not yet public. They took data, they scanned it. Should I tell the whole story? Sure. They scanned the data and did not properly look at the previous slides in the talk. I was asked to give a talk at NYU, scheduled long in advance, a week after they reported their results. I was a Princeton faculty member at the time, so took the train up. On the train, I read their paper carefully, looked at where they got their data from, and looked through it and realized they used the wrong value for what was the amount of dust in the galaxy. They made a factor 2 mistake. I was pretty sure about it. And I gave a talk at NYU. At the end of my talk, I said, And this bicep result was on the front page of the New York Times. I said, I'm nervous about this result. I think they did their dust analysis incorrect. My colleague David Hogg used this thing which I hadn't heard of before called Twitter. He tweeted that I had said I don't believe the results. The next week, I was at Harvard giving a talk. Immediately, everyone was really angry at me. How could I doubt their Nobel Prize winning result or deserving result? And I spent a couple hours talking with people there. And on the train ride from Boston to New York, I composed a 10-page email. Now, you have to understand my emailing habits. My usual emails consist usually of 2 words. I try to, I get a lot of email, I get even more now, and I try to be as succinct as possible. Now, if your senior thesis advisor sends you a 10-page email detailing his concerns and what you need to do, my recommendation is to read and answer the email, which was not done. So I then asked my graduate student, Colin Hill at the time, now faculty at Columbia, Raphael Flauger, postdoc working with me, now faculty at UC San Diego. I said, we've been looking at dust before, and let's reanalyze their data. And we did. Got up at the American Astronomical Society meeting, where I was the plenary speaker in Boston, and laid out the case of why that result was wrong. They have since withdrawn that result. It's been confirmed by Planck. So I think we have paid attention to, we're very conscious of the need to have control on dust. So that's why we have about 6 frequencies in this experiment. So we'll be able to correct for this. So, and I think this is, well, I was really annoyed with the bicep people at the time for how they acted. Looking back on this, I think this is actually really healthy science. Important claims are made, other groups test it, new experiments go and make the measurements. The Planck data, when it became public, made it very clear it was dust. The Planck team did an analysis showing that. In the end, the bicep team withdrew their claims, and science advanced, right? Important, this is, I think, one of the healthy correcting natures of science. When strong and someone makes a claim and it's not important and wrong, doesn't matter that much. Someone makes a claim and it's important, other people go and test it. And that's what happened here. And another important part of this, and this is, especially since I'm in Washington, I think open data is an important part of the story. Because if one of the policies that I think NASA has really been at the forefront of is the idea that data should be open and available. And when you have that and important claims are made, it's relatively straightforward to test.
Carl, use your microphone.
Oh, well, when will the analysis be done of the first results? So far, we've just got like first light and the telescope focuses. It's going to take some time to optimize it. We probably will not begin science run for about a year. The first science analysis will probably be based on the first year data. It will take us probably 1 to 2 years to do that. So it'll be 3 to 4 years for the first results. That's just the nature of these things. You saw with a lot of these experiments, they may run for 10 years. We've got now, one of the neat things about the experiment is with the funding from NSF, we now are building solar panels. It'll be almost entirely a solar-powered telescope that vastly decreases our operating costs because we don't have to deliver a diesel truck every other day. Of course, vastly lowers our carbon footprint, also makes it much lower risk. and as a result, makes it cheaper to operate for the long term. So we'll probably collect data, I think, for 10 to 15 years at the end of the day, because our sensitivities just grow and we can replace the detectors. So I think we will have the first papers in 4 years, and we'll probably be producing papers for 15 to 20 years.
Is it worth noting who it was and then he wrote a book about it?
Sorry?
Is it worth noting who it was and he wrote a book and he was a speaker here? And he's also the
Brian
PEI.
Keating? No,
Yeah. He's
no. Oh, Brian started Bicep, but Brian was not the one who made those mistakes.
Oh, he wasn't.
Oh, absolutely not. Brian, in fact, was effectively pushed off the analysis, which is why they made, well, one of the reasons things went wrong.
But he's now the PI for the
For Simon
Simon
Yep,
Observatory.
yep. No, but Brian was not the one responsible.
How about Casey after? Or do you need a comment on this? Oh, could you give him the microphone for a minute?
So just very quick questions about the ACT. What altitude is it at?
17,000 feet.
Wow. So is it mostly run remotely?
No,
You actually have people on site. So water
Yeah.
is a problem. Water is probably a limiting resource, not energy.
no. There's water. Water's easy to bring up. Just drive up there.
Yeah, just not to bring trucks, but 17,000 feet. Wow. So you are above even Mauna Kea. You're above maybe what, half the atmosphere.
So when we first went there, we would just acclimate and go up. Now we have these oxygen tanks. It's actually much safer. But the people who went up originally all complained. I don't have to wear these things. But it's you really notice it at 17,000 feet.
When I go to Mauna Kea, which is 14,000 feet, about half the people there get altitude sick.
Yeah.
So, and you're even higher.
Yeah, but we usually spend the night in San Pedro de Atacama. So you're spending several nights at 10,000 feet, and then you adjust. So it's actually easier to go there because you're 10, and most of the observers are living at 10,000 and going to 17. So it's only people like me who come as the theorists who comes as a visitor to the site,
Go straight up.
who goes straight up. My own experience is I thought I was fine until I started to take the 3 steps up the ladder, and boy, does it hit you right then.
You feel it here, or did you feel it here?
Like,
Did you feel it in your head? Were you dizzy, or was? Oh.
so,
I'm sorry.
Stand up, your name, that whole ritual.
I'm Frederica Dorima, and I'm a member. So you said many thought-provoking things, and my question is regarding the Big Bang. And you postulated, let's put this as 0. But that kind of, in a sense, violates the causality principle, right? That something must have been there before, and whether it was a collapse of the universe and we have an oscillating, and the physics maybe are very different and we don't observe what this physics generated. However, would there have been echoes of previous expansions and previous collapses, and can we detect those, or how we can disentangle them from all the signals we get, for example, if they're there?
Yep. No, you've hit on one of the big debates we have, right? Which is, if the universe started at that moment, how does it causally end up so uniform?
Right.
So let me give you 3 different answers. We don't know whether any of these are correct. Could be something else. One possibility people talk about is kind of a quantum foam, that we should think about this as a coherent quantum fluctuation. My favorite version of that is there are different ways of thinking about quantum mechanics. The way we are usually taught is that quantum mechanics is is not predictive, that there's randomness, but it's a local complete theory. You can actually trade off locality against predictability, and this is what's called pilot wave theory, and work done by, and I think there are some formulations built on that idea that you start with. You give it a causality, you get out locality now. So it's now you can start with a coherent fluctuation. That's one possibility. Another possibility is that if the universe is not infinite, but a finite compact universe, and it's negatively curved, then that can homogenize itself if that emerges as a quantum bubble initially. Another possibility, which is the one that I think you've asked about in your question, is that there is a pre-Big Bang that you had lots of time, it collapsed to get down and reach some maximum density and bounced again. And we don't understand how the bounce would happen. But my former colleague, Paul Steinhardt at Princeton, has been one of the big advocates of this. It's sort of a classical GR version. Neil Turok, who's at Perimeter, has a quantum mechanical version. So we think about this. And as you asked in your question, we try to look at the observational implications of this.
Can we disentangle if there are echoes? Maybe they have attenuated so much and we cannot detect them, or they are so much kind of, there is a coherent interference or destructive interference, and so the signals have changed completely, which may change also from our observations and our kind of deductions if this is happening, right?
So if we can study how the fluctuations were generated. If the fluctuations were generated in this collapsing phase before the bounce, then we don't expect to see gravitational waves, so we wouldn't detect them. And the fluctuations have a property of being slightly non-Gaussian. What do we mean by that? The hot spots look different from the cold spots. It wouldn't be symmetric under reversal. If the fluctuations are generated during this inflationary expansion, then you'd expect to see gravitational waves, and it would be symmetric under hot going to cold. So we're, as our measurements become more sensitive, we're looking for both of those effects, and people think hard about what other signatures might there be to distinguish this.
Thank you.
Let's move to a few questions from the live stream.
Hello. So I've got this first question from Paul Hess, who is a member. He says, will the upcoming gravitational wave detectors give us early universe data to combine with CMB? And if so, what additional insight might it provide?
So the primary target of gravitational wave detectors like LIGO is gravitational waves from merging black holes and neutron stars. Now, there's a space-based experiment called LISA that NASA and ESA are planning to launch in the coming decade, roughly, maybe longer. That, again's primary goal is looking at supermassive black holes, but has the potential to detect the background kind of noise from gravitational waves from the early universe. So depending on how the fluctuations vary with scale, LISA might be able to see that signal, and the combination of LISA and the microwave background will put on a more global constraint on how the fluctuations vary with scale. So one of the things when we look at the temperature fluctuations is how the fluctuations vary with scale. That was my fifth parameter that I didn't talk about that much because it's a little more mathematical, but that's what we would use for LISA plus the microwave background fluctuations.
All right, so second question is from Sharavan Rao, who is not a member. Are there any leading theories for resolving the horizon problem?
So by the horizon problem, what I think what people usually mean by that is, why is the universe look the same over there as it does over there? And by over there, I mean what it looks like in the microwave background, not that part of the ceiling and that part of the ceiling. And those two regions of if the universe did not go through an inflationary phase, have never had time to interact. And that's the horizon problem. And the inflation model is one resolution of the horizon problem. The models with the bounce, where you have time in the collapsing phase, also resolve the horizon problem.
What, is that it? Blue micro? You don't have to turn it on. It's on. It's on.
David Rosen, member. What are the laws of thermodynamics the same throughout the universe and at all times? And with those three models for flat, local spreading, not collapsing, are the laws of thermodynamics the same?
We believe so. That's one of our assumptions. The laws of physics are invariant in space and time. And the laws of thermodynamics are actually ones that we have in some sense more confidence of, because in many ways thermodynamics is sort of statistical laws, right? So what we wonder more about is, could the strength of gravity be stronger in the past than today? Could the strength, is the mass of the electron the same over there as over there? Thermodynamics, a lot of it, we could understand it in terms of just how things average out when you have many, many collisions. And we think those will be the same everywhere. Now, if the physical interactions vary, maybe not, but our simplest assumption, which seems to be validated as best we can, is the laws of thermodynamics are the same everywhere. One way of thinking about that, actually, as you phrase that question, is when we look at the microwave background and look at its temperature distribution, which is the black body distribution, we see the same black body distribution over there as we do over there, which suggests that we're seeing the same laws of thermodynamics over there as we do over there.
Think a blue microphone back there. And then if we can get a red microphone over here to Erica up in the front.
Are we for the blue? Yes.
Blue, yes.
Yeah. This is a lecture on the early universe, and I have a curiosity about black holes and galaxies. As which comes first? Does the black hole suck in the matter, or does the matter condense into a black hole?
So our current theories suggest that the galaxy should form first, and the stars in the galaxies collide to make black holes. That's what we think should happen. But this is something we want to test. And, when we look with James Webb, we can see really the earliest galaxies, and we see the galaxy history. I mentioned the LISA mission that looks for distant black holes. And LISA has the sensitivity to see black holes earlier than James Webb has seen galaxies. Now, if our theories are wrong and black holes form first, LISA will see things before James Webb. If our theories are correct, the black holes LISA sees will be later in the universe's history than the earliest galaxies. We have our current ideas based on our current theoretical models. They're plausible, but one of the reasons we do these measurements is to test these ideas. We don't know till we look.
Well, let's go to the red microphone. Now I think last question, blue microphone.
Hi, Joe Curry's not a member. I just had a kind of a more speculative question. What is your thought on the theory of eternal inflation, where you kind of have localized observable universes in a larger hyper-expanding universe?
Yeah, so this is an idea that says this period of exponential expansion, most places doesn't stop. So, I mentioned this idea that the universe just starts expanding really, really quickly. We have to live in a patch of the universe where it stopped, because we're not seeing, the universe isn't being stretched exponentially now. And there has to be a long period of normal expansion. And if you think about the universe undergoing a phase transition and being trapped in this false vacuum state, like superheated steam or supercooled water. This is the problem about going to a sauna with a physicist. I kind of walked in and it's like, I told my girlfriend, the steam's condensing on my body. This is just like a phase transition. It's like inflation. We're making it condense. So in the theory of external inflation, most of the universe is expanding exponentially. That takes up most of the volume of the universe. And we just happen to live in a region that's a rare region that's not undergoing that enormous expansion. And there's sort of what we people call an anthropic argument, which is we must live in that region because life could not exist if it was expanding exponentially. We don't know what the right. Eternal inflation's a plausible idea. I find it, and this sort of anthropic argument that comes around it, to be aesthetically unappealing to me, because it makes a universe have an enormous volume, and it makes it in some ways a very unpredictable model, because you have an infinite number of discrete regions, each with different properties, and we just happen to live in the one that's right for us. It reminds me of Pangloss, that this is the best of all possible universes and everything is for the best. And the universe has all these properties that are not necessary for our existence, in the sense of it could be a universe just with atoms and we would exist just fine. So I have aesthetic personal problems with the internal inflation. I would like there to be some clear observational test that would disprove it, so it's not just my own feelings that says, I don't like that model, and I'm going to work on other models.
Hi, my name's Erica Kane. I'm a member of the Society. And I wanted to hark back to an earlier slide that you showed regarding how we determine the geometry of the universe. So you tied that into hotspots and the observation of the hotspots as to whether or not we were seeing them too small, too large, the right size. And it was not clear to me, you may have said it and I just missed it, how, I think you said that they appeared to be the right size and therefore we were likely to be flat. How do you know that you're seeing them at the right size?
Oh, that's in a sense straightforward what I do with my, let's go back. Oh, wrong way. Yeah, so we look at the angular size of these fluctuations. We just measure what is the typical size of a spot here. The way we do that statistically is we look at this plot, forget the units, the amplitude of fluctuations versus scale. And you can see the fluctuations peak on this scale, and that corresponds to a degree, and that corresponds to the flat case. So we actually do an analysis on the map. Another way of looking at that analysis is, I think I showed it this way, as looking at stacking up the hot and cold spots. And what we measure is the angular size of this spot and the angular size of that ring. And measuring those angles gives us the answer.
But you have no other observation to compare it to.
We do. We have the observations of the distribution of galaxies and measuring that length scale. So we actually get a pretty coherent set of measurements. The question is, do we need to know the total mass of the universe to get an absolute scale? We need to know the density of atoms to get an absolute scale, more than the mass of the universe. We can either get that from the microwave background observations by looking at the thickness of the ring, which measures how much the photons diffuse relative to the electrons, which depends on their density. We can also look at the abundance of deuterium. I mentioned that deuterium is produced in the first few minutes of the Big Bang. Hydrogen burns to deuterium, deuterium burns to helium. Deuterium abundance is a result of incomplete burning. If you can have enough time, you make it all the way to helium. So the deuterium abundance gives us a measure of the atomic density, which is bang on the measurement of the thickness of that ring. So we can get sort of two independent ways of measuring the density of atoms. That lets us calibrate the ruler. Then it's the ruler we use for that geometry. So we sort of we try whenever we can to get at these things in multiple ways to check for sort of consistency in our model, because we're doing something pretty ambitious. We're trying to talk about the first moments of the universe. And we could be wrong in our assumptions, so you want to keep checking them.
Well, thank you so much for this. Before you go, we just have a few thank yous. They're actually real things, but so the audience can see them. We have of the announcement of your talk, signed by all the members of the General Committee on behalf of all the members. A signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, which explains why it was founded and has a nice description of what they thought discourse on scientific results should be, which actually mirrors what you were saying about what happened with BICEP 2 results. Before we go, we have a few announcements. The 2496 meeting will be the annual Joseph Henry Lecture and will be on May 17th. The speaker will be Brent Seals of the University of Kentucky, and he'll be speaking about how he has been able to read ancient scrolls. And if you think this is easy, here they are. Well, you probably would have thought they were what's left after you had a fire in your fireplace and the logs didn't completely burn, using X-ray tomography and artificial intelligence. And I think this is really important if we can read these scrolls in the majority of what they have to offer, because they offer the possibility that we'll be able to recover original texts of the Greek philosophers that we've never seen and only know about through the writing of others. Masaharu Tsubakura was scheduled to speak on May 31st, but he has had to reschedule, and we're going to have him a date in the fall, and we're arranging for a substitute speaker. 2498th meeting will be on June 14th. Speaker will be former NASA Administrator Mike Griffin, who is currently co-CEO of Logic, spelled with a Q, and recently testified for a different scaled-back approach to land the U.S. on the moon rather more quickly than he thinks we're going to get there on the current Artemis program. 2499th meeting will be the last of the 20 lectures of the 2023-2024 lecture series, and will close out the spring semester. It will be on June 28th, and the speaker will be Ben Schneiderman, and he'll be speaking on human-centered AI, ensuring human control while increasing automation. The 2500th meeting will be on 6th September. Assuming all goes well, a gala event, and I will have more to say about that later. The 2501st meeting will be on September 20th, and we don't know who that speaker will be. 2502nd will be on October 4th, and the speaker will be Mark Ockrand, creator of languages, and he'll be speaking on, in particular, Klingon. I'm hoping he won't speak in Klingon because I won't understand. But he has written an opera in Klingon and a dictionary. But he says there are other people who are more fluent than he is, which I find a bit strange. The 2503rd meeting will be on October 18th. The speaker will be Alexandra Gade, professor of physics and scientific director of the Facility for Rare Isotope Beams at the Michigan State University. Her office is in the cyclotron building, and she will be speaking about the facility, the structure of nuclei, magic number violation, and related subjects. We will post further commitments to the website as soon as they are set, so please check www.pswscience.org frequently for updates. Finally, let's thank everybody who worked hard to put things together. Again, please return the name badges, and with that, I will accept a motion to adjourn the 2495th meeting to the social hour. Second, all members in favor? All opposed? Meeting is adjourned.